the president of the local chapter of the Netherlands. Today we have a speaker all the way from Austin, Texas in the USA, where he is a team lead at the TechNet group. I'll talk a little about that later. But before we start the meeting, I would like to point out this meeting is being recorded and will be published on the EAGE YouTube page, just so that you're aware. All right. Well, let's go on with today's agenda. I'll briefly talk about the EAGE community, and we're one of the local chapters. We're part of the EAGE community, but EAGE is of course much broader than just us. There are a few announcements, particularly related to one of the upcoming conferences, and then we'll continue on with today's program. And at the end, there will be opportunity to ask questions, of course, and I'd like to thank the people that made this event possible. So, about the EAGE, the European Association of Geoscientists and Engineers, a non-profit. It has approximately 19,000 members worldwide throughout all of the major continents. And well, it supports the technical community through various means. There's the membership, which will allow you to join conferences, annual meetings, courses, and there's also support for events and for other grants through their PACE program. So if you are not a member yet, I would highly recommend you go on. You can simply go to eage.org and find out more information there. Now, part of the EAGE community are the local chapters. We are the local chapter Netherlands, but there's many throughout Europe and also abroad, further abroad. We collaborate often with the ones in Europe, especially when there's online events. And well, aside from that, we also like to look a little bit broader than just the other local chapters, such as the chapters that are related to the Society of Exploration Geophysicists. And of course, also the student members represented, for example, in the Netherlands, through the Delft Organization of Geophysics Students at TU Delft, which we have a close relationship with. Now, if you're interested in joining the EAGE community, I would recommend you look at your nearest local chapter, wherever you are. You can do so through the website of EAGE. Many of the chapters have a LinkedIn page, like we do, and have email addresses, and membership is usually completely free, and it helps us to make events such as today possible. We generally communicate all of our news through our newsletter, which you can subscribe through by sending us an email at eagelnetherlands@gmail.com. On the website, you can also find out some more information about the chapter and about some other event that we're involved with. And well, that is sort of to wrap up our introduction. Before we start with the actual event, I would like to point out that the EAGE is organizing the Near Surface Geoscience conference this year in Naples, Italy. The way that the conference works is it consists of several sub-conferences, shall we say, with focuses on different topics, for example, mineral exploration and mining. This year, there's two new sub-conferences, one on UXO and object detection, and the other one on geohazard assessments and risk mitigation, in complement with the ones that have been taking place for a few years. The way it works, if you register for the Near Surface Geoscience conference, you can attend all of these sub-conferences, so you can attend the entire program, particularly for the two new sub-conferences. They are looking for people with interesting ideas to present. So if you think this is interesting, I highly recommend you consider submitting an abstract. You can use the QR code on screen, and we will also send around some more information about this later. All right, with that being said, I would like to move on to the meat of today's program. The talk by Dr. Yangkang Chen, who, as I mentioned, is taking time out of his busy day in Austin to join us. And his talk will be on a decade-long journey in revolutionizing passive seismic monitoring. After the talk, there will be opportunity for some questions and a discussion. And we aim to keep this event about an hour, because we are aware that staying online for these kinds of things, especially so close at the work time, can be a bit draining. All right, so who is Yangkang Chen? Well, he currently is a team lead in machine learning and AI research at TechNet, which is part of the University of Texas. He also got his PhD from the University of Texas in Austin and was briefly 3 years, a professor at Zhejiang University in China. I'm sure I pronounced it wrong, so my apologies, Yangkang. But thank you again for joining us today. And his research focus is now mainly on how to use AI and machine learning for various geoscience problems, which we will see some of today. So with that, I would like to hand over the floor to Dr. Chen. Well, thank you for your attention.
Thank you very much, Yuri, for the introduction and for having me here. I'll first show my screen. This one. Here we go. Can you see my slide?
Okay, yes, we can.
Okay, yeah, let's start. Today, I'm very glad to be here to talk about what my team has been doing in the past decade on the topic of using AI for passive seismic monitoring, specifically for our earthquake monitoring, because that's really the main duty of TechSnet. Before starting my slides, the whole point of this talk, in my opinion, is that for achieving something really amazing, like make AI for production, for real-time monitoring stuff, we really need a persistent attitude to make a lot of progresses along the way. And many seemingly trivial and incremental advances will pay off at the end, right? So Rome is not built in one day, is the main idea of this talk. And this idea applies not only for earthquake monitoring, but for almost all the other subjects. This slide gives a brief outline of my talk. First, I would like to acknowledge a number of people, and then I'll show you some really amazing, fascinating results as a takeaway message. Hope you can remember my talk by these two slides of magic results. And then I guide you through a long journey, a decade-long journey for how to make AI in production and really benefit our daily life. And then lastly, I'll focus on the latest picker, which is EQCCT and its application in Texas. First of all, I would like to acknowledge a number of people who contributed significantly along the journey. These include many colleagues and many students and postdocs who work tirelessly to make this magic happen. And then here, particularly, I want to mention the whole TechSnet crew, because without their daily effort for preparing a lot of labels, for preparing the catalog for us to benchmark, and this presentation is impossible. So I would like to acknowledge all this contribution and help. So here is a takeaway slide for all my presentation. We have, simply speaking, we have applied AI for production and for near real-time passive monitoring in Texas. Here, I want to highlight that the meaning of real-time is definition dependent. If we define real-time monitoring as a latency scale of seconds, that's very high level. And then the real-time monitoring is still on the way, and hopefully will be out this year. So stay tuned. If we define the real-time as a latency scale of minutes, we are already achieve it. So, for example, for this slide on the left-hand side, we show a map for which we have applied our AI for near real-time monitoring. And our right-hand side, we show a magnitude comparison between the AI catalog and the manual catalog. And on the top, we see the magnitude difference distribution. We always see that most magnitude errors are around 0, right? And we see a mean and standard deviation as very small value. And on the top panel, we see like comparison between the AI magnitude and the preferred magnitude, which is provided by human. And specifically, I want to highlight that for magnitude above 2 earthquakes, we made no mistake. The recall of magnitude above 2 earthquake is 100%. So that's really amazing, robust. That's really the reason why we can make it in production and as our daily baseline method for daily operation. So because of this level of robustness, we can make it happen. And then here is another magical result. So here we really show the enhanced detectability, dramatically enhanced detectability using AI method, right? So for this slide, on the top left, we show the famous magnitude frequency distribution, where we can see 3 colors: red color, yellow, and gray. And red denotes the manual effort, right? The best of the human knowledge. And the yellow corresponds to the best of the state of the art, which is based on an optimized STA-LTA method. Right? It's pretty good. And also, before I want to mention, before the arrival of AI, here this yellow one is the baseline model for us for manually picking the arrivals. And after AI, we see a big change from yellow to gray, and we can see a dramatic change. Note that this axis is not on the normal axis, on the logarithmic axis. So like it actually improves a lot, like at least 10 times more earthquake detected due to AI. And on the right-hand side, we show daily distribution of the events. The same thing for different colors. And from traditionally manually picking less than 10 events per day to less than 100 per day for optimized STA-LTA to right now around 400 events by AI. So that's really a dramatic change. And on the bottom, we show the daily distribution and magnitude distribution, right? So the axis is the dates. And as we can see, the red one are mostly for large magnitude events, right? And then for the yellow one, we have some large and we have some moderate large magnitudes. And for the gray one, they are mostly small earthquakes. And we may notice a very particular special day here. This day we have a large magnitude 5.4 earthquakes happening in West Texas. So that causes a huge number of aftershock, right? And what's special here is that because of AI, we can detect a huge number of pre-shock events. So that's really an indication of something abnormal might be happening next day. So this really have a very high scientific value. Right? And this slide, I want to state the problem. So what is the exact problem we are solving right now? So the problem is simple. Pick the P wave and S wave. Right? For example, this red one, red verticalized, and the blue ones, they are P wave and S arrival. And these 3 panels correspond to 3 components seismograms. So all we need to do is to pick a P wave and S wave, like this. And based on these P wave and S wave arrivals, we can use the follow-up analysis software or workflow to do all the other follow-up tasks. And then I'll guide you through a long journey for the decade-long progress for AI. And the currently ongoing AI boom really started in early 2016. Right? We probably still remember that. So on that particular day, the company called DeepMind, they announced big news that their AI player, AlphaGo player, beat the best of human player for the first time in history. And then that news really ignited the curiosity of the whole world, including mine. Right? So everyone was thinking about what they can do to leverage AI for their research. At that time, I was a distinguished postdoc at the Oak Ridge National Lab, we were doing a very ambitious project using FWI for solving the Earth's structure for the whole world. Right? So the briefly speaking, the idea of FWI is to iteratively fit the observed data, 3-component seismogram, by iteratively updating the model parameters. And because of the scale of the problem, our problem is so large, we want to scale up to 6,000 magnitude above 6 earthquake. That's really huge amount of computation. One critical component is to select a window, right? To select those windows with a reasonably close observed and synthetic data. We cannot throw all the data into the inversion because it will explode. We can only select those good waveforms for inversion. So that's really the first ML problem for me at that time. And then I come up with the idea of extract several features, mostly physics-based features, to extract those features and use these features together with a shallow machine learning network to do the classification for picking the waveform, right? And next, so we, because we are at that time, I was a beginner in the field of ML, so we just use a multi-layer perceptron method to solve this problem. So the input is those features, those 5 features, physics-based, with many training samples. And then we go through this relatively simple network, and then we achieve the goal of classifying the waveforms into usable and unusable. Right? And back in the day, almost 10 years ago, we really don't have any resources for waveform picking or for earthquake detection. There's nothing at that time, right? So I need to develop everything from scratch. So here is a screenshot for the machine learning library I wrote at that time. And as we can still see that the first commit happened like almost 8 years ago. So that's really what I was doing at that time. Right? On the right-hand side, we show a class of the the neural network-based picker, right? And then we apply this simple method to the real problems, and then we compared with the at that time the state-of-the-art method, the FlexWin method. These blue windows correspond to the selected windows, right? As a matter of fact, this machine learning method works pretty well, and it actually detects some previously missing waveforms. Anyway, it works. And then we keep going. One disadvantage of the previous mentioned method is that it requires the synthetic data, right? All we need to, but we really want to skip the synthetic data, because for the global seismograms, to generate the synthetic seismogram is a huge amount of computation, and then not many people can afford that. And then the first trial is leveraging the clustering method. So the clustering method, the idea is that we manually we define some features based on some physics, right? And then based on these extracted features, we extend the data from a low dimensional space to a high dimensional space, and then we can use clustering algorithms to cluster those samples. And on the right-hand side, we show a simple example, right? For clustering method for STA LTA as a comparison for the same data, right? For STA LTA, for example, for this one, it fails to pick the correct arrival, but for the clustering method, it seems working pretty effectively. And on the right-hand side, we show the 3 features we use for this problem. So first is mean, second is the power, and the third is STA-LTM. Right? And really, the STA-LTM method is just based on this feature. Right? As we can see, this feature has a lot of oscillation, so which makes the picks inaccurate, right? So it makes sense. But for the clustering-based method, because we have more features, we can have a more robust result, right? So that makes the pick correct. And we apply this method to different types of real data, including some pretty challenging results. For example, for this microseismic data with very strong noise, and in this case, we did a pretty awesome job for this dataset, while the STLTM method just failed in this case. The same thing for real earthquake data. This is earthquake stack data, similar to our reflections and common short reflection seismic data, right? And again, the clustering method works pretty well, while STLTM failed. And based on the same similar idea, we can even extract waveforms, not just the peaks. If we can extract the waveform, and then we can do more things like time reversal imaging for passive seismic monitoring. So here we use similar features, but we change the SDLT to other like spectral centroid, because we think the spectral centroid is more sensitive to the waveform content, while the SDLT features is more sensitive to the arrival information. So in this case, for detecting waveforms, we defined a new feature called a spectral centroid, and this updated method works also very effectively. For example, for this microseismic data, we effectively detected the primary waveforms, and with zoomed field here, right, we see that most waveforms are reasonable and correct, and we can do the time reversal imaging for the whole data set or the carefully selected waveforms, and we can see a difference on the source location image. Well, if we import all the data into the framework, inversion framework, we don't get the focused location. Well, in this case, the image is more focused, right? Indicating from this perspective that the extracted waveforms are reasonable. And we keep going. And then in 2019, we developed a new method with a much with more features. In this case, we use 191 features. The idea is from the speech recognition field, right? Because for human voice, acoustic signals, speech signals, they are much like our seismogram. So we borrow some ideas of extracting features, like 1D features, like 2D features from their field. And then in this case, we define like large feature database. We still use the traditional shallow learning. In this case, we use a spot vector machine, and again, this strategy works pretty well. And for example, for this training field data, and we have labels here, manually pick the labels, and we can apply it. Applying the trained SVM model to testing field data, and then we obtain pretty good results. And we also compare 1D and 2D feature, combine the 1D, 2D features with the 1D feature only, and we see that there are differences. The difference mostly come from the coherency. For using 2D features, we can make the result more coherent, right? Which makes sense. And on the top right, we show the significance or importance of different features, because we did some analysis. We see which features more important, and in this case, it can guide future development of methods with more specific and more important features, right? But that's about future research. And our first attempt of using CNN, which is literally the real deep learning approach, is to strengthen the peaking performance, especially for very noisy data, right? And for example, on this slide, we show an example. The clustering-based method works pretty well for most cases if the signal-to-noise ratio is not that low. And for example, on the left-hand side, but if we boost the noise, this clustering method may fail, right? Which makes sense. And then we come up with an idea of combining CNN with clustering method. So the idea is simple. We use CNN to first detect candidate segments, and then combined with clustering constraints, we can get a better, more robust picking of the arrival, even for low signal to noise ratio cases. And this slide shows a comparison of different methods. For example, for STLTA, which is really the state of the art, and then for the gaming clustering. The difference is that we incorporate more features into the clustering. And on the right-hand side, we show the idea of the CN, combined CN and KC method. And in this case, we first do waveform classification, and then we select those candidate waveforms together with the constraint from the clustering, and then we can get a more robust classification. And on the left-hand side, we show the principles and the workflows for waveform classification. And in this case, we show a comparison of different methods for synthetic data and real data example. On the left-hand side, we show the very interesting test with respect to the increasing noise variation. Right? As we see that as the noise becomes stronger, the clustering method becomes less and less effective, where the CN and the KC method is still pretty robust, right, in this case. And for example, this is the synthetic data and real data example. I just skip it. So here is a very interesting noise test, noise sensitivity test. So we all know time frequency transform, and we also know that a lot of people use time frequency transform for improving deep learning. So why it's the case? So here we explain everything here. So for the same data, we have different levels of noise, okay? And as we can see that for the low frequency part, for the continuous wavelet transform domain, they are more or less the same. The only difference happened in the high frequency, right? So as we increase the level of noise, we mostly change the high frequency part, while the low frequency part is almost unchanged. So that's a whole point of using time frequency transform for improving deep learning, because it helps us to distinguish between high frequency and low frequency components. Right, so that's the whole idea. And then we include the time frequency transform in the waveform classification, and naturally we obtained even better and more robust results. So I have introduced quite a number of approaches. What's the remaining problem? The remaining problem is that the model is not generalizable. So remember, all these data that I show are not that challenging, not that large scale. They are pretty small data set, local data set. But what we really want, we need to be ambitious. We really want to make it really generalizable, train a model and apply it to everywhere in the world, right? So how? We miss something, the big data set, right? So we need to compile a huge number of samples representing the characteristics from all over the world. So that's really why we began the relatively ambitious project at that time. In end of 2020, we started the Scale Up Deep project. So there are two reasons for the name of Scalar Deep. First of all, we apply a time frequency transform, as I mentioned. It helps to distinguish the high frequency and low frequency components. And secondly, it's very deep. As we can see, this is a very, very deep network, mostly composed of convolutional filter. And for this one, we have 24 million parameters. It's a pretty deep and large network at that time. And we use a 7 scale for the scalegram. And a big advance for this project is that we make it generalizable for the first time. And we apply it to 4 areas, 4 dramatically different areas: Japan, Texas, Egypt, and Arkansas. Right? We apply this model, a pre-trained model, to all these areas and obtain very encouraging results. So that's the advance of this project. And then this slide shows a couple of examples for different cases for the results. For example, for short duration event, for a quite noisy event, and for one malfunctioning channel, and for a long duration event, and for cases we are actually outperforming the manual picks. And this is for another malfunction channel, and this is for teleseismic event, and this is for multiple events in one window, and this is for two malfunctioning event. And so for two malfunctioning channels. So all these examples show that this scale deep model can be effective for almost every type of data, right? And we also do benchmark comparison because during the software development or methodology development, really need to do benchmark so that we know which method is the best for certain data sets or certain criteria. So in this case, we compared with 5 other benchmark methods. 2 of them are template-based, the FAST method and the template matching method. So as we can see, so for the template-based method, they detect more events than the deep learning-based method. But it is reasonable because we need a template to help detect the very low amplitude events. But compared with other more independent methods like the CRED method is really the first generation of EQ transformer method, well-known method. And the 2 other methods are STA, LTA, with different implementations. We found that our deep learning scalar deep method is the best for all the independent methods, right? But still, less competitive than the template-based method. But template-based method requires the template, and that's also a disadvantage. And then in 2021, the transformer architecture started to dominate the AI world, right? And then we started to thinking about how we can apply a transformer to our problem. So here we show an integrated framework for simultaneously detecting the earthquake and doing magnitude estimation. Right? So we compile all the tasks in a very seamless way. So the input is continuous data, and then we output the P wave and P wave peaks and the magnitude simultaneously, which is really a very effective and efficient framework. And this slide shows the comparison between the magnitudes manually picked manual magnitude and AI magnitude for the California dataset and the Texas dataset. And as we can see, the predicted magnitude and the ground truth magnitude are pretty close, indicating it's a quite accurate framework. So here now, a question may be why we only pick P wave, right? And the answer is we pick P wave mainly for the purpose of earthquake early warning. And here I want to briefly mention the idea of earthquake early warning. So the goal of earthquake early warning is to issue an alert to take immediate action to save life, to save loss after an earthquake happened, but before the most destructive S wave hit the ground. So in earthquake early warning, every second matters. So we are only allowed to pick the P wave because the time difference between P wave and S wave can be up to 10 seconds or even 20 seconds, depending on the geographical distance. So in this case, we are really allowed to use P wave information. Although in a daily operation, we can use S wave information, which is the later topic. So for earthquake early warning, in addition to the peaks, in addition to the magnitudes, we need the hypocenter location so that we can calculate other earthquake early warning related parameters like PGA and stuff. And here we further develop a location algorithm using AI. So in 2 cases, if there are no sufficiently large calculable events, like in Texas, we don't have so many earthquake events as training labels, and we numerically generate the travel times at the synthetic data, right, using 3D retracing or solving the Econo equation for the travel time. And as long as we can generate a large training database, we can train a model, and then we input the observed differential travel time, and then we obtain the location in a very quick wait less than 1 second. And if we have a sufficiently large catalog events like in California, in Japan, and then we can directly use the real data for training such a location model. Right? And this case, we use Japan as example because we have a huge number of events, and the travel time measurements are sufficient for us to train a model. Right. So here, this slide really shows the distribution of the training and the testing data set. Let's go to the result side. So this slide shows the result for the location. Look, this is original scale, and then we zoom in a little bit and even more. And on this map, we see different symbols. The red dots correspond to the catalog events, and the blue circles correspond to the estimated location. And then those triangles are stations, and those black lines are the arrows. The difference, the black lines connected the station to the events, so on the left-hand side, top two panels, one shows the arrow distribution, the location arrow distribution along the Japan, the whole map. We see that unsurprisingly, we have relatively small errors in the inland areas, and we have a relatively large distance error in the coastal areas, which makes sense because for the inland areas we have a higher read density, we have more training data, and along the coastlines we have a smaller read density, so that we have a larger location error. And then I want to use the rest of my time for introducing our latest picker, the EQCCT. So here is a brief introduction about the EQCCT, right? So CCT stands for Compact Convolutional Transformer. So the idea of using CCT is that we want to combine the benefits of convolutional filter and the transformer architecture, right? Just to mention a little bit about the background, for the convolutional filter, the advantage is that it is fast, but it is less effective than transformer for dealing with time sequence data. But for the transformer architecture, it is quite effective and accurate for dealing with time series data, but it is quite slow. And then in this case, we kind of combine advantage of convolutional filter and transformer and try to make this CCT a lightweight architecture, but with a fast and accurate performance. So that's the key idea of CCT, and that's why we use it. The idea, another big question is why using EQCCT, why we consider EQCCT the best architecture, or the method is that we along the journey in the past decade, we almost tested all the possible methods we could try. Right? For some of them, I already introduced, and for some other methods, like this one, capsule network, I can skip some of the previous trials. So just to give you an idea that we have tried many architecture, and we did a very robust benchmark comparison, and then we found that EQCCT seems the best for this problem. So that's it. So here is a simple illustration about why CCT is preferred than the convolutional transform, convolutional filter. So suppose we have a phase to recognize. For convolutional filters, if we detect those key components like eyes, nose, and mouth, as long as these components are in the face, we consider it as a human face, regardless of their internal relationship, like this, right? So this is a face. Obviously, it's wrong. But for transformer, we consider their internal relationship, not just the component, but also their internal relationship, the position of the components. And then in this case, transformer is way more effective than CNN for defining this is a face, right? So that's a key principle of transformer architecture. And then I will go through quickly some of the exciting developments and application in the state of Texas. So here I show several examples of putting the arrivals on top of the waveforms, right? So for each figure, left and right, for from top to bottom. So the very top one is the probability of the P wave and S wave, right? So we can see two spikes. These two spikes really correspond to the P wave and S wave arrival. And below it, three components seismograms, and we show comparison between the manual peak and the AI peaks, right? So for example, for P wave, we see that these two dashed lines, one for manual, one for AI, they are almost overlapping with each other, even in the zoomed view, right? For P wave and for S wave, right? So they are almost overlapping with each other, meaning that the peaked P wave and S wave are accurate, right? And the same thing for the other events. And this slide is for large signal-to-noise ratio events. And then we also show the result for moderate SNR events. In this case, pretty much the same thing. And then we can even increase the noise level, make the SNR even lower, and then we still obtain quite good result, the overlapping peaks. And also, we want to do a robust benchmark comparison. So we compare our EQCCT model with two other most widely known methods. One is FaceNet, one is EQ transformer. And then we show the error histograms on this slide. Intuitively, the more centered the histograms around zero, the less error or the more successful performance it is. So in this case, we have EQCCT has a very tall histogram around zero, and indicating that for this dataset, EQCCT performs best over FaceNet and EQ transformer. And the EQCCT as the previous scalar tip is also highly generalizable. We apply it to different areas around the world. In this case, we also include Italy dataset. And this slide shows the performance for the Japanese dataset. Very briefly, just to show three waveforms. So yeah, as we can see, the two dashed lines are overlapping with each other between the manual and the AI peaks. So they are very accurate. For Japanese dataset, so for Texas dataset, we can see the noise level becomes much higher. But again, we seems to perform quite well, right? For this dataset, and the same thing for Italy dataset, right? So I'll go through quickly. And for different dataset, for different method, EQCCT, EQ transformer, and FaceNet, we have the best consistently. For all these testing areas, we have the best performance for EQCCT than the other two widely known methods, EQ transformer and FaceNet. And for us, and here is a very interesting application in microseismic application. So here I want to highlight the key challenge for microseismic application. One, the sampling rate is dramatically different. Right? So for broadband seismic station, the sampling rate is normally 100 hertz, but for microseismic data, the sampling rate can be 500 hertz or even higher. And that's what number one challenge. And number two challenge is microseismic data are mostly generated by hydraulic fracture, which is not including in the training database, right? So it's really a good case to test the generalization ability for a trained deep learning model. And on top of these two challenges, we also have the very geographically different location because microseismic application really a small area and all over the world. So geographically they are quite different. But in this case, it seems that the EQCCT performs quite well. And here I also want to mention that for microseismic data, we normally don't have the manual picks, right? Except for in the industry, we pay for labor to pick the arrivals manually. Otherwise, we only have the semi-automatic picks. Semi-automatic picks means that we use automatic picks to pick the arrivals generally, and then we manually quickly make sure that these picks are more or less accurate. So that's it. So which means that for the semi-automatic picks, they can be wrong, right? It can be not very accurate. But in this case, we show two scenarios. The first scenario on the top one, we show that the deep learning pick and the semi-automatic pick are reasonably close, right? For this event, for the P wave, for S wave, and for two other cases. And on the top panel, well, actually we show the cases where deep learning outperforms the semi-automatic picks dramatically. So in this case, the semi-automatic pick differ quite a lot from the deep learning picks. But in this case, we found that the deep learning picks are more accurate. And here is another test we call a choppy data application. So in this case, we do not apply the picker on continuous data. We apply to segmented catalog data. We extract waveform according to catalog. We just apply different pickers, and then we use location to verify the accuracy of the picks. And in this case, for example, we applied to Midland area of Texas. We found that for majority of the events, the location is accurate compared with manual one, except for several outliers, right? Like less than 10 in this case, which means two things. First, for majority of the events, the location and the picks are very accurate for deep learning methods. On the other hand, also very importantly, AI or deep learning is not a penalty. It can make mistakes. So that's really very practical for us. We can use AI, but we really need to be cautious that because they really can make mistakes.
Yangkang,
And also,
sorry to bother you. We need 10 minutes for questions. So
okay,
maybe
yeah,
you can quickly wrap up.
Yeah. Sure. Yeah, not too many slides left. So now we keep going. We keep making the picker for near real-time earthquake analysis based on the sophisticated workflow, and then we can show get pretty good results on continuous data, right? And here is a slide showing the difference between the catalog using different different location algorithms. We found that the better location algorithms, the more clustered events, right? From left to right, it's just a matter of different locator. And then we also show the location. These steps are really very standard workflows for normal earthquake monitoring. And here is event visualization. And then for another one, so here is a comparison between the AI and the traditional picker. Traditional picker is STA-LTA. We found that AI is more powerful in detecting very small magnitude events. And this is show the network density sensitivity. Right? What if we do not have such dense network, and how many events will we detect? Right. So this type of density study, and then here is like fault delineation. We plot the catalog in the depth slice so that we can see clearly those beautifully delineated faults. And we also compare the faults on the map view before using traditional manual effort and then the deep learning effort. We see that for very short period of time, we can delineate the fault structure very well because we have detected more small earthquake, and also the GitHub repository for most of the results. We can reproduce all these results. And here is also advanced for us. We compile a Texas test set for AI. So it's really very meaningful for us to fine tune the model to make it even more powerful in a specific area, including Texas, right? And here is the slide we see in the beginning. And then Finally, the second last slide summarizes advantage of EQCCT. So it performs better than the state of the art, and then it obtains good statistics on benchmark data sets and highly generalizable and help similar locations. So the location is quite accurate. And this brings us to the last of my presentation. So along the journey, when we look back, what are the keys to success of AI to make it mature, production ready? So first is, as I said, data is super important. We have two distinct stages. 2021, right? We have some progress, but slow. And then later on, we have huge amount of data. And then we make very fast progress. And then benchmark comparison is very important. Right? We do AI not just for AI. We want to demonstrate that it is distinctly better than the state of the art. And then also teamwork. And as you see, all these results are not from my own effort. It's a teamwork. We need earthquake science people, machine learning, software development, visualization, right? And also the courage for making it production and making it real time is very important. Lastly, Rome is not built in one day. And that's it. Thank you very much.
Well, thank you, Yangkang, for the presentation. Yeah, I see a lot of very interesting results, and I believe somebody is already interested in asking a question. I see that he has had his hand up for a while, so if it's time to ask a question.
Yes, thank you very much for a very beautiful talk, and congratulations also on achieving the results that you did with so much, with such a concerted effort over many years. I had two small questions. First question was, after the CNN, you went to the Scalo Deep, and you said that it was the Scalo Deep was the first model where you were able to generalize it. Yes. What was the key there? Was it just sheerly the number of parameters, or was it the number of scales that you used in the continuous wavelet transform? What was the key there?
Yeah, good question. Good question. So transforming from a CN, relatively shallow CN to Scalo Deep, the key is we have a huge amount of data. We have like thousands of times larger data set. We need to train a model using this large data set. We need to make the network deep. That's the only reason we need to make it deep. As long as you have a very large data set, you cannot make the network very shallow, because otherwise you cannot obtain a very good performance. So that's the only reason we need to make it deep.
So the key was really making it deep.
The data, because we have way more data.
Okay.
Yeah.
Okay. And another question that I had was, all the way in the beginning, you showed in your results slide, you showed that you picked the detectability, that you detected a lot more small earthquakes, and you said you saw a lot of precursors before the main event, the 5.4 event in Texas. But I noticed also that right after you see also a lot of, it wasn't that, right here. It didn't seem that you see a lot of very small earthquakes just before. I mean, they seem to be continuous in time, right? There's no telltale signal there, or.
Yeah, that's a good observation. So in this case, my guess is that because of the large magnitude and 5.4, like record high earthquake in decades, because of the huge release of energy, we have relatively fewer small earthquake. So in this case, actually, it makes sense, in my opinion, because we already release a huge amount of energy by these guys, and naturally we have fewer small earthquake. That's a very interesting scientific observation, actually.
Okay. Yeah. Thank you.
Thank you for the question, Huub. I see Jaap also has a question. So Jaap, please go ahead.
Yes, can you understand me?
Yes, perfectly.
Well, the question I have is, to get good pics, maybe you need to know something about the subsurface below your station. So how do you handle that? Do you try to find the shallow subsurface in the area first before you apply then special picking methods?
That's a good suggestion. we haven't considered about the side effect on the performance of picking. That's in our daily operation. That's related to different problems about like estimating the PGA for hazard management and mitigation. For picking itself, we just treat all the station the same. Like we compile all the station regardless of their geographic location. We just treat them the same and then throw them into the training, and then we obtain a model and then apply to all these stations. Although these stations from different geographic location represent certain regional subsurface information, especially, for example, like a very typical example is the noise. The noise and the signal characteristic are dramatically different for different areas. We think that these type of characteristics are automatically captured in the training process. So we don't need to like very carefully, deterministically to characterize this such a subsurface information. I think all the data bear all the information you mentioned.
So could it be that, say, if you want to determine the horizontal and vertical location of a particular earthquake, then actually you need to have some sort of velocity model. So how do you get that information?
Yes, good. That's good. Then I understand your point. All right. So the for the whole process, the workflow of earthquake monitoring, the picking of P wave and S wave arrivals is the only step that requires significant human interference. And as long as we have a pretty good and reliable P wave and S wave peaks, we use a fairly robust automatic framework to associate the events and then to locate the events. All these steps are done automatically. And regarding the velocity model, yes, we need a velocity model, and the more accurate velocity model, the better, of course. And for our current real-time and baseline implementation of earthquake location, we use 1D velocity model, and we use a location algorithm called nonlinear lock to locate earthquake. And then we are based, except for the deep learning based arrival peaking, we are based on the SASCOM software, which kind of the state of the art of the industry scale earthquake monitoring workflow. So we all the efforts are put into the to improving the arrival peaking, and we do not we just let all the other later on components the same as traditional. And what traditional do, we do the same.
I wait, and I might come back with another question later, but let's give other people a chance.
Thank you very much.
If there are any other people who want to ask a question, feel free to unmute yourself and ask.
Well, I have one more, but maybe Jaap first wants to go if nobody else has one.
No, you go ahead.
Yeah. Is the software available for? Is it open source or not? Or the EQCCT?
EQCCT, yes, it's open source, and the SASCOMP is licensed software.
Which one?
The SASCOMP. SASCOMP is this licensed software.
So you need the SASCOMP for the EQCCT?
No, for EQCCT, for the peaking, arrival peaking, we just rely on EQCCT. And then we output the peaks, the output from EQCCT to the SASCOMP software for association and the location.
Okay.
Yeah.
Thank you.
Mm-hmm. But we can rely on also other open source association software and location software. There are many open source options, but here because in the in the viewpoint of a statewide seismic network, we need to make sure the results are the best. So we use relatively more robust network like SASCOMP for doing such job. We can substitute all the following steps, association location with other method, no problem. It's just a matter of like tiny difference on the accuracy.
Okay. All right. Thank you very much. Thank you.
Okay,
Thank you.
then I'll take the chance for the last question. Is normally you read that if you use very many attributes, then the algorithm usually get confused. So what you then apply is principal component analysis, or as you did yourself, to see which attributes are really contributing. So your 89 or whatever, 69 attributes, that seems amazing number.
Yes. Go to this slide. Yes, this slide.
Yeah.
Yeah.
It
Yeah,
didn't
that's
bother
this.
the algorithm.
Yeah, this inspired the idea from the speech recognition field. The kind of like using these features for their purpose, but still in the traditional way. And think I understand your point. I totally agree with that. So that also becomes one disadvantage for traditional methods, including the shallow learning methods. But the beauty for deep learning is that those features, those important features, are automatically decided, so that we can make a more effective decision.
Okay, so it only maybe then involved more compute time if you use many attributes like that, but the CNN knows how to form
Yes,
sort of
yes. The whole idea of deep
calculated
learning is
attributes from that.
to extract the features automatically.
Yeah.
And that's all the encoders are doing. The encoders are used for extracting features, and then the decoder are used to combine all those features and then make a good decision.
Okay, thanks.
All right. Well, I think with that, it's a good point to end on. Before we leave, I would like to take over the sharing of the screen, if possible. Again. Yes, there we go. I would like to point everybody to the next event that we have planned in February, on February 27th. We will organize an event together with Clearwater. Gabriel Rizzuti will come towards the TU Delft, where this event is sponsored by the Delphi Consortium towards scalable uncertainty quantification of seismic universe problems with deep learning. So more information about the exact room will be spread soon, but in the meantime, you can already register via the QR code or the link in the email that has been sent around. And then finally, I would like to thank everybody for their work. I want to thank Dong of our chapter for mostly setting up this event. I want to thank Yangkang for giving this a wonderful presentation and sharing his results, as well with TechNet for allowing us to have the presentation. And I want to thank all of you for taking the time out of your busy day to attend this. Thank you very much, and see you for the next event.
Thank you so much. Yeah.
Thank you.
See you guys.
See you next time.
Thank you.
Bye.
Thank you very much for organizing it, Yuri, and thank you for the presentation.
Well, thank you for joining. Yeah.
Bye.
Bye-bye.